Welcome to Physical Attacks and Countermeasures, the 9th session. Today we deal with some advanced power analysis attacks. You have seen DPA, CPA, and have seen the discussion about power models and some other features of each of these attacks and the limitations and so on. And then today we see some other sophisticated and advanced attacks that they can, in some cases, overcome the problems and issues of classical attacks. The first attack that we want to see is mutual information analysis. It is also sometimes called MIA, M-I-A. And the motivation of mutual information analysis actually is not to make any assumptions about the probability distribution of the Sarton and leakages. Now, if you remember what we had before, we supposed that in CPA and DPA, the noise can fit into the Gaussian model. Yeah? I mean, you get an average and then there is a Gaussian distribution around the average. And then using, for example, DPA, because it was checking just t-statistics or applying the t-test, checking the average of two groups. Again, it's assumed that the noise is Gaussian and then the leakages are different from their mean or estimated mean, which is average. And the same is in the CPA because the correlation actually, or correlation coefficient examines the linear dependency between the hypothetical values and also the real values. Now, mutual information wants to get rid of this. And at the same time, what is important is that in CPA, what we discuss again, the linear dependency between the hypothetical power values and the real values. And mutual information wants to relax this necessity. It means that you don't need to have a linear dependency. Any kind of dependency should be actually recovered. In some cases, as we will see later, mutual information analysis is able to relax the power model, means that relax the hypothetical power model. Means that you don't need necessarily to consider Hamming weight or Hamming distance or anything. Sometimes you can perform the attack without any power model. We will see. Before explaining how the MIA works, we need to review something about the statistics. First of all, in Shannon entropy is calculated like this. The entropy of X, random variable X, is the sum in a discrete form, is the sum, sigma, of probability of the value, all possible values of X, probability multiplied by log 2 of the probability, and then you sum them up and the result should be negated. And of course, if it's not discrete, then you have a integral, over all possible values of the X, or from minus infinity to positive infinity. Now, what is the meaning of entropy? Entropy says how much information in the variable is uncertain. Somehow it's called also the level of uncertainty. The level of uncertainty means that how can you predict the value of X knowing its entropy? Then the level of uncertainty says that if the entropy is high, is the maximum, then the value is absolutely uncertain. Now in a discrete domain, suppose that you have an 8-bit value, and suppose that the 8-bit value is uniformly distributed. Again, this is the distribution, and this is the value of the X from 0 to 255, 8-bit value. And this is the probability of X, and suppose it is uniformly distributed. And what is this value? 1 over 256. The entropy of a random, uniformly randomly distributed 8-bit variable is 8. The maximum entropy that you can get. Means that in this case, the entropy of X is 8. This is a level of uncertainty, maximum level of uncertainty. Means that by looking at a distribution, you cannot guess what should be or what is the most probable value. Or you cannot guess the next value. For example, you have a lot of samples of X, and then you cannot guess the next sample. But if the distribution is different, yeah, for example, is somehow like this, then the entropy becomes lower than 8. The entropy of 8 is the maximum and is for uniformly distributed. Means that this is fully uncertain. But here is a bit certain. Means that the values which are between this, yeah, they are more probable. They are more probable than the other ones, than this one and then this one. Then the entropy becomes a bit lower, means that the level of uncertainty is also lower, means that you can somehow say or guess that what is the next value if you sample from this distribution. Then entropy is what? Is the level of uncertainty. I guess you have used often some programs to compress files, for example, zip file. Do you know how the zip file works? It's exactly based on entropy. Yeah, what it does? First, you have a large file and you want to compress it. Suppose that for the file that you give to compress is analyzed, yeah, based on every 2-byte value, yeah, 2-byte values, yeah, and then, for example, you say 0, 0, 0, 0 hexadecimal, and then the frequency you write here, how many times it appears in your file, yeah, every 2-byte. For example, it says 30 times. And then the next one is 0, 0, 0, 1. And then, for example, is 1 times. No? And then 0, 0, 0, 2 till what? Till F, F, and F, F, for example, is 60 times, and so on. Then this is sorted. Yeah, this is sorted. Then, for example, something comes here. The most probable one is, for example, C010, for example, is 150 times. And the next one is F0, F1 is 140 times, till something which never happens, for example, or 0001, which happened only once. And then the highest probable one will be shown by lower number of bits. Yeah, for example, this one with 2 bits. Yeah, and this one, for example, also with 2 bits, till you can, for example, show 2-bit values, and then afterwards it becomes 3 bits till end. Then when you want to show C010, this one, the first one, then you don't spend 2 bytes or 16 bits, then you spend only 2 bits. Yeah, and so on. Then the size of the file will be smaller. Of course, this table should be also given at the start of the file to decompress it. But this works if the entropy of the file is low. Yeah? This is exactly the what? The distribution. If you divide this by the number of 2-byte values that you have in the file, this will be the probability distribution. And then it happened for you that sometimes you wanted to compress the file, but it could not be compressed because the entropy is very high. When the entropy is high, you can never compress. I mean, you don't gain by compressing. Even the size of the file will be larger because that table should be also come at the start of the file. Now, this is the concept of this is also based on the entropy. Now, you can have also the definition of entropy for 2 or more variables. Then you need to have the probability distribution of the, or joint probability distribution of 2 random variables, and the same way, yeah, and then log 2 of this. And then you have to go through all possible values of x and y. Yeah, this is not something special. Yeah, means that you just replace this p by the joint probability distribution, and then you have to go through all possible values in x and y. And then you can also define the conditional entropy. Of course, you can Do it other way around means that you can say P of x given y, and again log 2 of P x given y, and you can say the conditional entropy is the same as the joint entropy minus the entropy of the second random variable. Now this is also the definition. And by this you have just the entropy and also joint entropy and conditional entropy. But what is the mutual information? The mutual information is defined like this. If you want to have the mutual information between two random variables x and y, the entropy of x minus the conditional entropy of x given y. And if you write it down, you will see that, okay, I mean the formula that we have seen in the last slide. This is the entropy of x plus entropy of y minus the joint entropy, which is the same as actually mutual information between y and x. Means that it doesn't matter if you swap x and y. I mean, this is the mutual information between x and y is the same as mutual information between y and x. But what is the meaning of the mutual information? It says, or it measures how many bits of information can be learned about the random variables having another random variable. It means that if you have y, if you know completely y, and you know the distribution of y, how can you guess or estimate the other random variable, the x? Now, there are two random variables. You have access to one of them. Then how much information you gain from x, having completely the y, which is the same as the other way around. Means that if you have fully x, how much information you gain about y. This is the meaning of mutual information. And as you see, it's only based on entropy, conditional entropy, and joint entropy. What is important? The mutual information between two random variables is 0 if and only if x and y are fully independent. Means that there is no relation at all between these two random variables. And the mutual information between x and y is the same as the entropy of one of them if x fully determines y. Means that actually they are absolutely the same. Means that if you have information about x, you fully get the information about the y. And if this is the case, then actually they are the same. Yeah, means that entropy of x is the same as entropy of y. Yeah, I mean the I of or mutual information between x and y is the same as the entropy of x and the same as the entropy of y. Yeah, means that if two random variables are exactly the same, the maximum mutual information is what then? The entropy of x. Now, how can we use this concept, mutual information, in the attack? This is what you have seen before, if you remember. For the CPA, we have seen this, that you have the plain text or ciphertext or data, and these are the key guesses that we had, and then we give it to part of the cryptographic algorithm, like, for example, Spock's output. This is what we have done. And then afterwards, we get the hypothetical intermediate values. For example, they are the Spock's outputs. And then we give them to the hypothetical power model, and we get a matrix of the same size, which is the result of the hypothetical power model based on these hypothetical intermediate values. And then these are our real traces. As we discussed before, the number of columns are not the same, but the number of rows are actually the same. The number of rows are actually D, which is the number of traces that we had, and the number of columns here is the number of key guesses, but the number of columns here is the number of sample points that we have in the power traces. And then the idea was that to compare in the CPA, compare the first row of this guy with the first row of the other guy, and again first row of here with the second row of here, and the first row of here with the third row of here, and every two column from the hypothetical power model and the real power traces should be then compared or correlated through the CPA, and then you get a singular value in this matrix saying the correlation. Now, if for the mutual information, is actually the same, means that instead of the correlation, we want to then what? We want to estimate the mutual information. It's exactly the same, yeah? Means that here, this column is a samples of one random variable, and one column of here is also the samples of the second random variable. And then we need to then estimate or calculate the mutual information. And the highest value of the mutual information should be actually showing us the most probable key candidate, because when the mutual information is higher, means that having information about one random variable, we earn information about the other random variable. We will discuss about this. This is more expensive compared to CPA and other attacks. We will discuss about this as well, that hypothetical power models actually can be anything. You don't need to use Hamming weight or some sophisticated power models or something which fits to the device specification or characteristics. Now, need to then show you how these attacks actually work, because this was a theory, and now a bit more practice. These are the traces that we measured, yeah? I mean, similar to before. Several of these traces we measured. Of course, each of them has one plain text, for example, if we consider the encryption. And then we look at one sample point, for example, here, and then we have a lot of samples exactly at this sample point, yeah? Then we know that we can have their distribution, means that at this point, we will have the distribution Yeah, for example, this distribution will be something like this. And what are these values? They are from the A to D of the oscilloscope. Yeah, they are our measurements from minus 128 to 127, right? This is a distribution, and what you can see here is some form of histogram, yeah? Because then you say how many times minus 128 happens, how many times minus 127 happens, and so on. This is a histogram that you make. I mean, this is the only thing that you can get from the digitalized data, the data that you got from the oscilloscope. Based on the key guess and based on the data that you have, like the plain text of the encryption, then you guess some intermediate values, like the Spock's output. No? As example, a Spock's of plain text X or K, and this is known to us, and this is what we guess. For one of these guesses, we know the output, of this intermediate value. Let's call it D. And then based on D, then you categorize them into several groups. Yeah, and then you may have also what? You may have a hypothetical power model, like the Hamming weight. At the moment, consider the Hamming weight. Yeah. And we call this H. And based on H, you say H equals 0 and H equals 1 till H equals 8. Then you categorize into groups, and then you get different distributions. One of them is something like this, and another one is something like this, and another one becomes and so on till you have another distribution for the last group. And so, what we were doing before, we were considering this as just sample point, and then we did not categorize them, but based on, we made another distribution. We made a long vector of the samples at this point, and then correlate them with the result of the hypothetical values. Now here, based on the hypothetical value, like the Hamming weight, for example, we categorize them into groups. And now what we can do, if you remember, what was the mutual information between X and Y was the entropy of X minus entropy of X given Y. Now let's call X the power values. And let's call Y the hypothetical values. Now, this Y becomes H, and X are these power values. Now, entropy of X, what is the entropy of X? How can I calculate the entropy of X based on all of this? X is here, right? This is a distribution. The distribution, I mean, currently what I got, the distribution based on the histogram, and I can calculate the number of frequency, then I got this histogram. Then histogram, of course, can be turned to the probabilities. And then I can calculate the entropy of X. How was the entropy of X? Entropy of X was minus sigma of all possible values of X, P of X by log 2 of P of X, right? This I can calculate over this distribution or histogram that I have. How about the second one? Entropy of X given Y. Y is given, you see? When Y is 0, then you have this. When Y is 1, then you have this. When Y is 2, you have the second one. When Y is 8, you have this. Then what do? Then you calculate here entropy of X given Y equals what? Here 0. Then you can also, similar to here, calculate the entropy based on this formula. Probability, and you get this. Then you get also here entropy of X given Y equals 1 till here entropy of X given Y equals 8. Right? But they are 9 different entropies. Each of them will be a probability distribution, because this is a probability, this is a distribution of X given Y equals 0. That means that you should not actually first get the probability based on this. You should not get the probability based on this and then turn them to probability for the given Y. Means that for each of them separately, then you have to calculate the probability and then individually and then estimate the entropy. Means that the sum of this distribution should be 1. Now, you got 9 different entropies. What do you do to get one singular value? You need a singular value here. You have 9 different entropies. What is you should probably have learned this during your bachelor about entropy, and now how do you calculate this? Because this is a formula of entropy of X given Y, but not for a particular value of Y. What do you do here? Then you multiply this entropy by probability of Y equals 0. Then you multiply this by the probability of Y equals 1. And this by the probability of Y equals 8. And what is this probability of Y equals 0? How many times H equals 0? Divided by the all number of traces that you have. This guy is the number of the cases that H equals 0 divided by the number of whole. Actually, this is the weighted average. Yeah, you multiply them by the number of times that they happen, and then sum them up, and then divide by the total number, yeah, weighted average. Then if you do this, and then sum all these values up, you get this guy. And this guy we already calculated, then you have mutual information. That's all. Now, this is mutual information analysis. Of course, you have to repeat this for what? For every key candidate and also for every point in time of the traces. There are few difficulties. First of all, these distributions, these histograms, this one, and also this one, and also this one, all of them. Now, these histograms, they are very sparse. Means that if you do not have millions of measurements, then you cannot feel these histograms. Most of them, the values are 0 and then some values somewhere. And if you have very low number of traces, like 100 traces, then you don't have a really distribution. Some values there, some values there. Now the attack will probably not work. Then what you should do, you should actually select the number of bins. Number of bins in histogram. Means that then you divide this. For example, you say, I want to have 10 bins. This is also, you guess. Then you divide the maximum value, the minimum value and the maximum value to 10 cases, and then say this is one bin, this is the second bin, this is the fourth bin, and so on. Then you try to fill these bins, then to have a distribution or histogram which is not sparse. Then you fix from one value to another one as the first bin, second bin here, third bin here, and so on. But then you have to take these bins for each of them also the same. Means that this will be also the bins that you have selected from the main distribution, and then you transfer the same bins or use the same areas for the bins for every of this smaller distribution. Then, for example, 9 bins, 10 bins, 5 bins, Then you have some factors. That means that you may select 5 bins and perform the attack, it doesn't work, then you have to change it. 6 bins now, then 7 bins, and then 8 bins, and 9 bins, or no lower number of bits, and so on. This is something that you can do. Instead of doing this, by selecting the bins, you have another option. The option that you can do instead of dealing with the histograms is to use kernel distribution. What is a kernel distribution? Having a histogram, you turn it to continuous distribution. Histogram is something which comes from a discrete data. 127, how many times? Minus 126, how many times? 0, how many times? This is discrete data. It means that between 0 and 1, you don't have any value. But continuous distribution is not something like this. Then what you do, you say, I have the distribution first. They're based on a histogram. For example, 1 value here, 2 here, and then nothing. And I have 1 here, and I have, for example, 3 here. Then to turn this histogram to a continuous distribution, you select a kernel distribution. For example, there are many different versions of the kernel distribution. I will show it later. But then you select, for example, this as my kernel distribution, which is a Gaussian distribution, for example. And then you replace this guy with a distribution like this. And you select this guy. Of course, you need to multiply them, the second one, to something larger. And this one to here, and the third one, the large one, into something like this. Then, of course, the result will be what? Will be something like this. Because then the sum of this, if you get an integral over this, if it's x and this is p of x, the integral of p of x is of course 1. Then you need to divide this also by the number of things that you have. I mean 1, 2, 3, 4, 5, 6, 7. Yeah? Then you divide it by 7. Then if you get the integral over all of this, integral over p of, if we call it here y, which is the sum of all of them, this should be also 1. How can it help you? Then you don't deal with discrete data, you deal with the formulas of continuous distribution. And instead of getting the sigma, yeah, to sum the values up to get the entropy, then you get completely the integral over this. For example, in MATLAB, there are some features that you define the function. For example, this is a function. Yeah? For example, you know the Gaussian distribution. You can have a formula for the Gaussian distribution for the mean and also the variance. For example, for variance, you fix a particular value for the variance of this, and you know that the sum of this is 1. And then you need to just change the mean, yeah, because this is the mean of this one, this is the mean of the next one, this is the mean of the third one, this is the mean of the fourth one, and then sum just these functions. No? I mean, for example, if it's the histogram of x, if I call it a histogram, the result of this y becomes what? Let's suppose that here x is, for example, 0, 1, and then here 4 and 5. Then histogram here y will be the h of x, because it's at 0, plus 2h of x minus 1, yeah, and then plus again h of x minus 4, and plus 3 times h of x minus 5. And then you need to divide this also by 7. Then, by changing the formula for the h, you can get the integral over this, not only this, to calculate the entropy. Then you don't do the discrete way, then you do it in a continuous way. I can show you one also paper which shows exactly this, the mutual information analysis, a comprehensive study. And there are some figures that might be interesting and useful for you. For example, you see here these things that I have explained. Yeah, they are the sum of these values, and then you get a distribution like this. Then this is also one example to turn one histogram into a continuous distribution. And here are some examples for the kernel distribution. For example, you can have uniform, this guy. Yeah, the uniform, the first one, which is similar to what we have seen, but you can have, you can write the formula for that, and then again use the integral to get or estimate the entropy, but it doesn't help you much because it's based on a uniform function. And then you can see that there is a Gaussian kernel here and the formula for each of them. What is important is this, the sum of this or integral over this should be 1, yeah? Should be adjusted to be 1. But there are many different types of these kernels that you can use to turn discrete distributions or histograms into continuous distributions. Okay, we talked about this. Now, what is the benefit of mutual information? If you remember the last, before what I have drawn, you know, we had some classifications based on the h equals 0, h equals 1, and h equals 8, you know, for example. And now suppose that we turn them into continuous distribution. You know, it doesn't matter, distribution is discrete or continuous, and then if you have distribution somehow like this, let's suppose the distribution is somehow like this. If you look at the average of this, and suppose that the averages of these distributions are different, yeah, then you see that, I mean, if you perform CPA or you perform DPA, if you classify them in two groups, you don't get any information. Because that even based on the correct key candidates, and if these distributions are different, correlation coefficient and also t-test doesn't give you anything. I mean, you cannot classify them correctly. But the idea of mutual information is that if these distributions are different, then we can actually find out for which case, for which key candidate, when they are categorized in a way that distributions are different, still we can catch it. Because the entropy of each of them is different now here. And if you classify them in the wrong groups because you selected the key wrong, then the most of distributions will be the same. Yeah? And then the entropy of them will be also very similar to each other. But one of them will have a different entropy, because the shape of the distributions will be different. And entropy of each of these distributions will be also different. This is the idea, that we should be able to detect any kind of dependency, not only in a case that noise fits into the Gaussian distribution, or we don't have any assumptions for the noise. One more thing, for the correlation coefficient, what we said, the result of the hypothetical values, these guys, should be linearly dependent on the values of the power consumption traces. Means that even if the distributions are based on Gaussian, means that one of them is something like this, and the other one is somehow like this, and this is also somehow here. For example, this is the mu of 0, and this is mu of 1, and this is mu of 8. Then the assumptions that we had for the CPA means that if you have mu 0 to mu 8 and h equals 0 till h equals 8, then this should be linearly dependent. One of them increases, the other one also goes high, or other way around. One of them goes up, the other one goes low. If this relation is not linear, then CPA is not able to detect it. For example, if you do not select a Hamming weight model, but select, for example, part of the intermediate value. For example, 5 bits or 4 bits of the SPOX output. 0 till 15, if you have 4 bits of the SPOX output, 4-bit value, and then you say, I only consider only this value, 0 till 15. But if you consider 0 till 15 as a real value, it doesn't have a linear dependency with the power consumption. No? But if you consider 0 till 15 as the 4 bits of the SPOX output and then perform the mutual information analysis, there is no fundamental reason that the attack should not work. It means that there is no necessity to have any relation or any really linear relation between the hypothetical values and the leakage of the circuit. They should be just based on the classification that you do. The power traces should be different, and they should not be different through the mean. Just the distribution should be different. That's all. There is also another limitations by this. I mean, what we say power model is not important. You don't need to use the Hamming weight model at all. It doesn't matter at all. You can use the intermediate values by itself. For example, let's say use the SPOX output, like 4 bits of the SPOX output that you can select, or some bits of the SPOX output. But somebody may ask, why not consider the entire SPOX output? For example, the 8-bit of the SPOX output. We have 8-bit. Why we do not consider 8-bit? means that the hypothetical value becomes 0 to 255, right? First difficulty is that you need many traces to fill these distributions, yeah, because then you divide all traces of one sample point into 256 cases, then the distributions might be again sparse. Another problem is that by changing the key candidate, you do not mix these classes. Again, the position of them will be different. You select the key equals 0, this will be, for example, the classification that you do for key equals 0. You select key equals 1, then these neighbor 1 becomes, actually they will be replaced because just one bit of the key will be different. Then the places of them will be different. Then the result of the entropy will be exactly the same. It means that for all key candidates, you receive the same value of mutual information. Again, you cannot perform any attack. Then you need to avoid some part of the intermediate values to perform the attack. For example, the maximum thing that you can select is 7 bits of the intermediate value, for example, for the AESS box. Why? Because the AESS box is a bijection. If this box is not a bijection, for example, this, I mean, we did not discuss a lot about this, but if I guess you have learned this during your study before. The boxes are not bijection. They are 6-bit to 4 bits, 6-bit input, 4-bit output. Of course, they are not in bijection because the number of input bits and output bits are not the same. Then you can directly select all bits of this box output. Because for mutual information, this hypothetical value or this intermediate value that you select, they need to be a many-to-one function. Yeah, many-to-one function. And a bijection is a one-to-one function. It's not a many-to-one function. But if this box, for example, has 6-bit inputs, 4 bits output, then what happens, of course, there are a couple of inputs, different inputs that they have the same output. Then there are many inputs that they are mapped to the same output. Then it's many-to-one function. Then for definitely you need many-to-one function. When you also ignore 1 bit of the box output is the same. Yeah? Then 2 inputs of the box will map to the same output if you consider 7 bits of the box output. Again, it becomes a many-to-one function. Fortunately, we do not give you any assignment for the mutual information. I can say that it's much more complicated than template attacks if you want to implement it. I mean, I don't stop you if you want to implement this. And there are many, many parameters that for some parameters the attack works, for some other parameters the attack doesn't work. Although you are performing the attack on the same device with the same traces and the same intermediate value and everything. Yeah. Now the advantages of MIA. First of all, it's independent of the distribution of the leakages. As we said, no Gaussian model is considered. And it can also detect any kind of leakages. It should not be only visible through the mean, for example, like the DPA and CPA. And it also avoids the necessity of having a linear relation between the leakage model and also actual leakages. This is also what we discuss intensively. And what are the disadvantages? First of all, it's computationally much more expensive than DPA and CPA, because DPA, as you learned, is just doing the t-test and getting the average and variances, and then you are done. With the CPA, you need to guess or estimate the correlation. We don't have much parameters to select. Here in MIA, you need pretty much more memory compared to CPA. And also, you should keep in your mind, if you have an attack working, you have a classical attack working, like a DPA or CPA, yeah, if it's working with some number of traces. Performing a mutual information analysis on MIA does not decrease the number of traces that you need if you have a working CPA or DPA. Usually it's the case. MIA is useful when the leakage of the circuit is not ordinary. And usually it comes from some countermeasures. And the countermeasures that we will learn later, they may change the way of the distribution of the leakages, then in average they are all the same, but in, for example, the variances are not the same, then the mutual information can be applied. You should not consider it as a general attack which works everywhere. Then instead of DP and CPA, I want to apply always MIA and the traces that I have. No, it's not the case. If the implementation is vulnerable to classical attacks, the classical attacks are much more effective than MIA. And then from my point of view, the most important disadvantage is that it has a lot of parameters, particularly for distributions. For histogram, you need to select the number of bins and also which area is every bin. This is also something that is in your hand and the hand of the attacker. And if you go for the kernel distributions, then the type of the kernel that you select, and then the way that you get the integral, they are all not that easy. Then we look at another type of advanced power analysis attacks, which is based on collision attacks. Yeah? The idea is somehow taken from what we have seen in the collision timing attacks. Means that collision in the AES, 2S box outputs are the same, then the 2S box inputs are the same, and then we recover the difference, the linear difference between two key bytes and so on. We use the same concept now in the power analysis. First of all, what is a collision? The definition of the collision, if two intermediate values are the same, then we say an internal collision occurs. There are many different types of these collisions. For example, 2S box outputs in one encryption rounds are the same. Or 2S box outputs in two different encryptions are the same. Or 2S box outputs in two different cipher rounds are the same. There are many different types of collisions that you can define. The idea is to find these collisions using sidechain leakages. And once we detected such a collision, then we learn some information about the key. Suppose now that two box computations have the same output. This is called linear collision in AES. Then what we say that, okay, the SPOX outputs in one round, the same round. For example, the first round of the AES, they are the same, similar to cache collision attacks that I explained. Then you say, if I know P1 and P2 and I detected this collision and one only collision I detected, then I can learn directly the difference between the keys. And if you have a microcontroller, we will see some examples. If you have a microcontroller which has a lot of sample points and a couple of clock cycles to do this lookup, this should actually ease finding this collision. It means that you have a lot of sample points and you have a lot of clock cycles relevant to these lookups, and you have a lot of also possibilities to detect this collision. In hardware, this is not that easy, particularly if you have one single clock cycle. And in addition to the SPOX, a lot of other things are also happening at the same time. Then you cannot look at the traces and say this clock cycle is similar to another clock cycle, then I detected a collision. Let's look at it like this, that one single SPOX is used for two different SPOX lookups. In software, for example. And this is the story that we had before. You have a vector of P1. And you have also power consumption of them, power consumption relevant to each of them, or corresponding power consumption. And then when the P2 is processed in software implementation, a couple of clock cycles and curves of the power traces, then you have some power traces when each of these lookups is actually processed or calculated. And then what you do, you try to see whether these two are the same or not, or these two are the same. Any two you can select, to check whether they are the same or not. Then you have to select one statistical tool to check whether these two are the same or not. And of course, this is not absolute. It cannot say that they are definitely the same, definitely a collision happened. You know that in microcontrollers, what we discussed, the Hamming weight of the data is very dominant. affecting on the power consumption values, then these two collisions that you may select, and say that, okay, this is the collision that I have detected, they may have the same Hamming weight, but not the same value. Then you detect the collision, but the Hamming weights of the, for example, the Sparks outputs are the same. Then you need to change your attack in the way that you do not actually recover the delta of the key, but again, you reduce the area of this delta of the key, because then you know the Hamming weight of the two Sparks outputs are the same. You don't know that they are exact the same. You don't just know that the Hamming weight of the are the same. But if you say that, okay, by any chance I recover that or find out that they are absolutely the same. For example, if in your traces the Spock's input and the Spock's output, both of them are there, means that in the power trace covers the Spock's input and also a Spock's output, then the chance that they have the same Hamming weight at the input and the same Hamming weight at the output is very, very low. Then it doesn't happen that much often that the Hamming weight of two Spock's inputs are the same and the Hamming weight of their Spock's outputs are also the same. Then you detect that two values that they are processed are exactly the same. And then you, similar to cache collision attacks, you detect a delta key, which is the difference between the P1 and P2, and the same are the difference or distance between the corresponding key bytes. This is known as linear collision attack, as I explained, but there are a couple of problems. The most important problem is the false positives, means that you detect a collision, you say these two are actually the same, and then you reduce your key space by this. But this is not true. For example, you selected the collision in the wrong way, then you may actually avoid or remove the correct key candidate from your list. Of course, this can be rechecked, means that you do not try to just find the key based on these two traces, then you have to try many other things and detect more collisions to be able to confirm what you have done. And then a couple of heuristics and ad hoc techniques have been used to handle these false positives. And if you are interested, you can read this paper, multiple differential side channel collision attacks on the AES, published at CHEST 2008. But what we want to do today in this session, we want to use some other schemes to detect more collisions at the same time. The scheme is called correlation collision attack or correlation enhanced collision attack. It's similar to cache collision. And this actually works, these attacks actually works if you have one module, like in hardware or software. In software is, for example, a lookup table, or in hardware is, for example, there's box, which is reused for the computation. We will see later if this is actually not reused, means that you have, for example, in hardware 16 different AESS boxes, a SEALA attack may work. But at the moment, consider that we have one single S box, which is used 16 times for one round. Like the serialized architecture of the AES, or it's a software implementation, then everything, of course, is sequential, and then in a loop, you apply the lookup table of the AES 16 times. As I explained, the same lookup table should be used at the moment. This is our assumption. Similar to cache collision attack, they can recover actually a relation between the key bytes, not directly the key values. Means that at the end, when the attack works in the best way, still you need to guess 8-bit of the key. Now let's see how the correlation enhanced collision attack works. This is what I discussed, means that a box is reused at one point in time. The P1 is given, and then XORed with a K1, and then it goes to the box. For example, suppose that this is power consumption trace or clock cycles, or one clock cycle relevant to this box computation. And in another point in time, might be the next one, might be far away, doesn't matter. Then P2 is processed. Then at this point in time, I write the corresponding power values for each of these plain text values. Now, if I measured 1 million traces, then P1 has 1 million elements, and the corresponding power vector has also 1 million elements. No? And then when the P2 is processed, I need to find out exact the same corresponding point. I mean, if they are 10 clock cycles away from each other, then I have to then move this guy to 10 clock cycles, and it's at the, for example, peak of the power traces. This should be also at the peak. Now I write also what? The power values of this corresponding to this point for P2. And now I have two vectors, each of them, for example, 1 million elements. And now the attack starts. The attack works based on this, that what I do here, I get average over these power values based on P1. For example, P1 equals 0, what is the average of the power values? P1 equals 1, what is the average of the power values? And so on. Then you get a vector of average power values with a size of 256, because the AESS box is 8 bits. And in the second one, what I do, I first guess the key and say delta k equals 0, 0. And now I calculate what? I get again average over this based on P2x or delta k. Now, delta k is 0, then I get the average of the power values. It's the average vector again, or mean vector. Then I say delta k equals 0, 1, and I get again average. Till delta k equals ff, all possible values of delta k, and I get an average. What you should also keep in mind, which is easier to do, once you calculated this with delta k equals 0, 0, which means you actually got the mean over P2, you don't need to recalculate the mean. This is the permutation of this guy, because you change the delta k 0 to 0, 1, then, for example, 0, 0 turns to 0, 1, 0, 1 turns to 0, 0, 0, 2 turns to 0, 3, and so on. They just will be permuted till the end. It means that averaging is required only once. Now, what we say, let's correlate these two vectors. Yeah? And then guess the correlation or estimate the correlation coefficient. And then you get a vector of the correlation values. And actually, the highest correlation value should show the most probable delta k. Why? Because if the delta k is true or correct, for example, if this one, delta k equals 0, 1, is the correct delta k, then you know P1 will be similar to, or is P1 equals P2 x or delta k. This is what we said. Now, if the collision happens, P1 plus P2 is the same as delta k. Then you can just write it other way around. Yeah, we say P1 x or P2 is the same as the delta k. Then you can say P1 equals P2 x or delta k. Yeah. Then, if delta k is correct, then the power values which is here should be similar to this one. That one which is here should be also similar to the second one. The third one should be similar to the third one here, and so on. Why we get the correlation? Because at two different points in time might be an offset. Or they might be actually amplified. Now, just the correlation will ignore all of them. I mean, you already learned that correlation coefficient between two random variables is the same if you scale one of them or you shift one of them. Then this will help you to perform the attack. What is important? What you can see here, there is no power model at all. No Hamming weight, nothing. What we consider here, the box is not involved at all. Yeah, this is just based on the plain text values and the delta k. There are advantages and disadvantages. First of all, we have no hypothetical model for the power consumption. This is what I just explained. And we don't have any heuristics to deal with the false positives. I mean, it's not like the first collision that I have shown, that we look at two power traces and then say there is a collision or not. And it's actually generic to examine the leakage of a design. It means that if you may perform a CPA and DPA, which do not work, but then correlation collision attack may work, because you're not able to select a good power model when you perform, for example, CPA. Because a CPA, as we said, needs a linear dependency between these two random variables. Then here there is not such a thing. We will discuss about these things later. First order leakages, I mean, through the average or through the mean. Means that a steel or assumption is that the noise is Gaussian. In these average vectors that we got, again, we completely ignored any kind of distribution. I mean, distribution can be any form. We ignore the distribution, we got the average. Means that we said when plain text value is 0, then we got the average. Then we ignored any other information which are available in the distribution. The disadvantages, you remember we discussed or explained a statistical moment, and I explained that the average is the first order statistical moment, right? And here, what we do, we are correlating moments to the moments. If you remember, here, this is one moment vector, and this is another moment vector. And then we are correlating them together. What is the size of this vector? Just 256, completely independent of the number of traces that we use. Then you should know that, I mean, when the number of elements in two vectors, when you estimate the correlation is low, then you have a very high error or inaccuracy, because there are just 256 elements. And it's even worse if you target a cipher which has a smaller S box. For example, there are ciphers like present. There are a few lightweight block ciphers, symmetric block ciphers, that they do not use 8-bit S boxes. They use, for example, 4-bit S boxes. And then what happens in the 4-bit S box, then the size of this vector becomes just 16 elements. Then you have much more inaccuracy in estimating the correlation. This is one of the disadvantages. And then it cannot be used as a metric, because if you perform an attack using 1 million traces, you cannot have any value of the correlation telling, okay, how many traces you need. I mean, of course, if the attack is not successful, then you say the number of traces that I have are not enough. But if the attack is successful, similar to, for example, CPA, you don't have any rule of thumb based on correlation to say how many traces actually you need to perform this attack. And then how hard the attack is. I mean, nothing can be said based on the result of a successful attack. For that reason, there is a successor attack, which is called moment correlating DPA, which avoids all these problems, which is a better attack. Similar scenario, I mean, I keep exact the same thing, means that here P1 is processed and here P2 is processed. I mean, I write the value of the P1 here, and I write the value from here to P2 here. And then what I do, then I get average from the first one. Up to here, the attack is the same as before. Now, what I do, actually, I apply a CPA using this power model. Means that I don't use any Hamming weight or anything else, but I use this vector, which is a mean vector over P1, and I use this as a power model to perform the attack on P2 when the P2 is processed. Means that here I guess the key, delta K plus P2, similar to before, but I calculate them and you see they are the same because delta K is 0. Now from this vector, for example, is 45, then I come to this vector, I get the 45 and extract the mean of the power value and write it here. And then for 9A, I bring it from here to down. And anyway, similar to CPA, this is the result of my hypothetical power values. which are taken from the mean vector over P1. And for delta k equals 1, I do the same till delta k equals FF or 255, and then now similar to CPA, then I correlate here this vector, which is the real power values when the P2 is processed, with the result of the hypothetical power values taken when P2 is processed, based on 1 delta k. And again, similar to before, you get a vector of the correlation, and the highest one should actually show you the most probable one. You know, if everything is fine, means that you have enough traces, the sample points are selected correctly, and so on. And it avoids all the problems that the other attack had. You know, means that it can be used as a metric, because then the rule of thumb that we had actually applies, because you have here the traces, and all these traces that you have play a role in the correlation that you estimate. And by increasing the number of traces, you can see that, for example, the correlation of the correct key candidates stays the same, for all the others are going down. Then in the correlation, as I said, then it's not restricted to the size of the S-box or the size of the mean, means that moments are not correlated together, or we are not correlating moments with the moments, we are correlating moments with the traces. But again, it's again first order moment, because we get here average. You know, this is something that you should consider. We will deal with that with the higher order attacks later. Something that I should explain you perform attack somehow like this, but you remember for CPA and DPA, we had to perform the attack on every point individually. Here we have to do the same, but we should keep the distance the same. Means that we perform the attack between here and here, but then we move this to one sample point to the right, and we move this one also one sample to the right. If the distance of them, for example, is 300 sample points, then we keep this distance and then move this distance, yeah, everywhere. All the areas that we think are relevant. For example, from here to here, and again, one sample point here to the right, and here one sample point to the right. The same until we cover everything. And of course, from this one, P2 also correspondingly moves like this. Now, the difference, I mean, correlating moments to the traces instead of moments to the moments, this is what I explained. It's similar to CPA, but moments are used as power model. You know, this is also what I explained. Instead of having a hypothetical power model, we have a model which is taken from the device by itself. I show you one example here in the slides, and also another example in MATLAB as before. There is a serialized implementation of present in the slides. Present is a very lightweight block cipher. It has, for example, you see here a state register, has just 16 nibbles. Nibbles is clear. Nibble is 4 bits. No? You remember the somehow the shift register of keylog cipher, which was rotated. Here you can implement it in a serialized way, that a box is calculated in a shift register base, but every clock cycle 4 bits are shifted. And this is the S-box. No? And in this particular example, the S-box is divided into 2 parts with one register in between. Yeah, and this is a small combinational circuit register and another small combinational circuit. And then both of them together makes the S-box. And then 16 clock cycle plus 1 clock cycle, because you have one register here, you do the entire sub-nibble or S-box operation, yeah, or S layer is called. And then in the present cipher, there is a P layer, which is a permutation layer, means that it takes this state register and permute the bits and slide it back into the same register. And the key in this example is just rotated, yeah. Again, 4 bits are rotated in the first encryption round. Then the implementation was hardware based on an FPGA. And if you look at the traces or one sample trace, this is the order: S-box 5, nibble 5, nibble 6, nibble 7, and they are also calculated. And then there is also an overlap between them. Because as I said, f and g, there are 2 functions. When f of 5 is calculated at the same time, g of the previous one is calculated. When 5 is calculated here, next clock cycle, 6 comes to this pipeline circuit, and then there are some overlaps. When you perform the attack between 5 and 6, then you need to keep the distance 1 clock cycle. Yeah, this is 1 clock cycle. They are the deviations of power traces. Yeah, I mean the clock cycles is here positive, 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 and so. Now, if you perform the correlation collision attack, you see that actually the attack works. I mean, if you are careful enough, yeah, the black ones is coming up a little bit, and you see the value of the correlation 0.9 because you have just 16 elements in the vector when you estimate the correlation using 50,000 traces between the box 7 and 8. Yeah. And if you perform the same attack using moment correlating DPA, this is what you get. You know? This is clearly different and is coming down when something else is processed. What is bad about the attack, what you can clearly see, is that similar to what we discussed, there are a lot of ghost picks here. There are a lot of other key candidates here that they are also high. Of course, the correct one is high, but there are some other candidates that they are also high. The reason for that is that, again, if you remember, there is no nonlinear function between them. Yeah? We have the P1 as the power model and P2 X or delta K. Yeah? By changing the delta K a bit, yeah, 1 bit, just a few things happen here. Yeah? Not very much the result will be different. And for that reason, you see a lot of other key candidates that they are also high. Now I show you the example in MATLAB. Here I have some traces, and I think I have 10,000 traces. I can plot one trace. Every trace has 5,000 sample points, and it's again from a serialized architecture. I can guarantee that the first round of the AES is there, but not completely. Yeah, similar to what you had already. Yeah. The first thing that you should do to perform either correlation enhanced collision or moment correlating DPA is to find out this distance between two target bytes that you want to process. Here, of course, I can plot the SNR. I mean, this is what important, what you learned. Then you apply SNR, and SNR based on the plaintext values. Yeah, this is what I actually also showed you. Yeah, I mean, then you don't have the key because you are performing the attack, but then you need to find out the distance between two clock cycles or 2 points in time that two targeted boxes, for example, are processed. Then for that, you calculate or estimate SNR based on the value of the plaintext. And this is the code that you have seen before, mean and the variance. And then you just, here I selected the plaintext values without knowing the key. And I estimate the SNR. And I selected here, just an example, byte 6 and byte 10. To perform the attack means that I want to get a delta K between K6 and K10. And if I run this, we have two SNRs, right? And if you see, they are actually processed right after each other. Yeah, means that there are two peaks. Of course, one of them is higher than the other one, and it's not as high as when, for example, 10 is processed. This is 6, and this is 10. Then what we should do, we should keep the distance between from, for example, here and here into the attack. And because we have many samples, yeah, in every clock cycle, then the distance between them should not be that accurate. You know? I mean, for example, if a few 2, 3, 5 points you are not selecting the distance correctly, it actually works still. Yeah. Now we should get the distance between them. Now what I do, I select one of the points here, which is 1037, and I select another one here, which is 1370. Now let me write them down. 131037. And what was the other one? 70. Now, and this is the correlation collision attack. I'm attacking byte 6 and byte 10 using 10,000 traces. And what I'm getting two vectors, mean and the variances. Of course, the variance is not necessary here. I mean, this is, it was taken from the SNR, but at the moment it considers the variance as well, but the variance can be completely deleted. Yeah, what it does here for all possible values of the input plaintext, because completely independent of the key candidate, we just get the mean vectors, because as I said, you don't need to guess the key and then for every of this delta key that you guess, recalculate the mean. You just calculate it once and then perform the attack. Here we are just feeling M1 and M2. And then what we do here, correlation coefficient is delta key, which is guessed from 0 to 255. And here is exactly P2 X or delta K. Now, by this, what I'm doing, I'm actually here correlating M1 at that sample point, which is I, with the M2, which is permuted. Yeah. Vector, you see vec, vector, this vector is 0 to 255. Which is actually the indices, what you consider here. Index is actually 0 to 255, but indices in MATLAB starts from 1, then this is +1, and this +1 actually happened for this here. 0 to 255 XORed with delta key that we guessed, and then +1 to make the index, and then at this sample point I, with the I plus time difference, and time difference was what we have written manually. And then at the end, you just plot the correlation. Let's have a look. It's now making the mean vectors. Now checking all delta keys. This is now the result. Now this blue one should be actually the correct delta key, which appears in 2 clock cycles. Why? Because again, probably the SPOX happens or has some register in between or some dependency in 2 clock cycles. We can also do the same or apply these changes to the moment correlating DPA, which is the same attack. And you see here we just do the mean vector once over only M1, and here we apply correlation over this vector again for M1, and then the t values, the traces by itself. We correlate the mean with the traces. Now, if we run the moment correlating DPA, it's slower. Why? Because there we were correlating small vectors, each of them 256. Now for every key candidate, we are correlating long vectors, and each one is 10,000 elements, because we had 10,000 power traces. Okay, now you see that the result is roughly the same as before, but look at the correlation, 0.15. And we look at this guy as well, which was 0.6. In this case, you don't see that much difference. I mean, both attacks actually work. But from this one, from the moment correlating, you can somehow estimate how many traces you need.